When a large language model gives you an answer, it feels like it's thinking. But what's actually going on under the hood? In this explainer, we're not going to focus on what it says, but on the raw mechanics of how it chooses every single word. Let's get into it. Okay, so we're going to start with a scene that's probably pretty familiar to all of us. You open up an interface, you've got a simple, factual question in mind. This is going to be our test case to really see the machine at work. All right, here's the prompts. The first human to walk on the moon was... Now, look, most of us already know the answer to this. But the interesting part, the real magic, isn't the answer itself. It's what happens in that tiny pause, that split second before a single word appears on screen. Right here, that blinking cursor, this is where the entire process happens. The model isn't off searching some database of facts. Nope, it's doing something much more fundamental, something based completely on statistics. So how does it actually select what comes next? Let's just freeze the system right here. At this exact moment, the model's only job is to complete the sentence. It's just looking at the string of words and that's it. And this is key. There is no check facts step. Its only goal is to predict the next most probable word. And this really gets to the core of how these models operate. They aren't engines of fact, they're engines of probability. They are built from the ground up to figure out what word is statistically most likely to come next based on all the patterns in the billions of sentences they were trained on. So what you're seeing here is a peek inside the model's brain, so to speak. It's calculated a probability for what the next word should be. It's not choosing an answer, it's just ranking possible ways to continue the sentence. Neil gets an 85% probability, not because the model knows a historical fact, but because in its training data, the sequence of words, the first human to walk on the moon is just overwhelmingly followed by the word Neil. And this is a really, really crucial distinction to make. That 85% is not a measure of how confident it is in the fact. It's just a statistical likelihood. The model is simply saying, hey, based on all the text I've ever seen, the word Neil is the most predictable thing to say next. Understanding that difference is why this all matters for us. So in this case, the model gives us a factually correct answer because the most probable linguistic path happens to line up with reality. The truth is just a byproduct of the statistics. For the model, probability always comes first. That's the only thing it cares about. Okay, so if the output is just a result of following the most probable path, what happens if we nudge that path a little bit? We can actually run a little experiment right now to prove that the model will follow any plausible path we set it on, even if that path reads it completely away from reality. Let's hit reset. We're going to use a new prompt. We've added a tiny but really powerful nudge, a woman named. Just like that, we've created a completely new linguistic path for the model to follow, a path that we know is factually incorrect. And would you look at that? The probabilities have completely changed. Neil is nowhere to be seen. The model is now giving high probabilities to the names of famous female astronauts. Why? Because in its training data, those names are statistically connected to words like woman and moon or space. It's just continuing down the new path we gave it. This moment right here perfectly shows the core mechanism. The model didn't stop. It didn't object or flag some kind of contradiction. There was no internal alarm bell that went off to check this against a historical record. It just did its one and only job. It continued the sentence down the most probable new path. By changing the input by just a few words, we completely changed the output. We didn't trick it. We just gave it a different starting point, and it followed the statistical trail from there. Probability overrode reality, because for the model, probability is its reality. So what is the fundamental mechanism here? When you strip everything else away, what you're left with is a surprisingly simple and repetitive loop. It's actually helpful to stop thinking of it as a reasoning engine and start thinking of it as the most powerful autocomplete system ever built. The whole thing is just a simple loop. 1, it takes the current sentence. 2, it calculates the probability for every possible next word. 3, it picks one, usually the one with the highest probability. And 4, it adds that word to the sentence and starts the whole process over again, word by word. That's it. There is no other step. The AI researcher Andrej Karpathy put it perfectly. He said at its core, it's just a glorified autocomplete. Now, it's a very, very sophisticated one for sure, trained on an unimaginable amount of text. But it's an autocomplete engine all the same. Its function is to predict what comes next, not to know what is true.
Okay, now that we've actually seen the mechanism in action, we can finally talk about a word you've probably heard a lot: hallucination. We waited until now to use it because you really have to understand the mechanics first to get what that term actually means.
A hallucination is usually described as the model making things up, as if it's an error or a bug. But as we've just seen, that's not really what's happening. The mechanical reality is just path-consistent text generation. The model is doing its job perfectly. It's just that the most probable linguistic path doesn't happen to line up with the facts.
So let's just do a quick replay of exactly what happened, step by step. It all started when the model was given an incomplete sentence. Its only job was to calculate probabilities. It created a ranked list of the most likely words to continue that sentence.
Then it simply selected the most statistically probable option from that list, which made the sentence one word longer. And at no point in that entire loop did it ever pause to check reality. The concepts of true and false just aren't part of its core calculation. There's only probable and improbable. And that brings us to the most important takeaway of all. The model's answers sound so confident because they are linguistically fluent. It's just really, really good at stringing words together in plausible ways. But that confidence comes from statistical fluency, not from a connection to the truth. This whole probabilistic way of working actually explains a lot of other weird behaviors too. For example, in our next explainer, we're going to look at why the model often just agrees with you, even when you're completely and totally wrong.